Hey y'all, in this lesson, I'm going to teach you some methods to prove trig identities. I mentioned in my previous video that it would be a good idea to keep a piece of paper or note cards as to have like a running tally of identities and theorems that we can use. So basically, the process for showing that two trig expressions are equal is called validating or proving trig identities. I showed some very simple examples in my last video, and these are going to be just a little bit more involved. But I'm just using some examples to kind of show you some methods to solve these problems, basically. As we get further into trig, these identities that we are proving are going to kind of help us to solve different harder problems. All right, so the first option is to change your terms into sine and cosine equivalents. So we have this equation here, and I can change tangent and secant into sine and cosine using my reciprocal or quotient identities. I'm going to leave sine x. I'm going to change tangent into sine x over cosine x. And then I'm going to change secant x into 1 over cosine x. So if you haven't already, just start getting these identities lodged in your mind. Have those there ready so that when you see those, your brain can automatically apply those and you can solve these a little bit quicker than having to pull out things that you can't remember. All right, and then I'm going to simplify where I can. So on the left side, I have sine x times sine x over cosine x. So I'm going to simplify that into sine squared x over cosine x plus cosine x equals 1 over cosine x. Then there's several ways you can approach this problem from here. You could change this into a fraction by getting a common denominator, or you could multiply both sides by cosine x to clear the denominator. I think I'm going to go with that one. There's not necessarily a right answer there, but I think I choose that one. Just pick one with confidence and choose it. Wherever you go, go boldly. All right. So now if I simplify that, the cosine x times this fraction, the cosines divide. So I'm left with sine squared x. And then cosine x times cosine x is cosine squared x. And then cosine x times 1 over cosine x is 1. Now, right here, that's the Pythagorean identity, and that is a true statement. So I could be finished, but I'm going to clean it up just a little bit. I know that sine squared x plus cosine squared x is 1, and then 1 does equal 1, and that's done. Since I ended up with the true statement, then I know that the original statement that I started with is true. Sine x times tangent x plus cosine x equals secant x. That's it. You're done. Okay, the next option is to use the Pythagorean theorem and other fundamental identities. So yet again, those identities and theorems are going to come back into play. So all of these things that we've been using and playing around with, you're definitely going to be seeing them again. So I want you to play around with this equation for just a second, pause it, play around with it, and see if you can get close to proving it. I am going to have to apply a little bit of my fourth method here. I'm seeing a cosine x in this term and this term. So I'm going to pull that out by factoring. So cosine x comes outside, and that leaves me with 1 minus sine squared x equals cosine to the third x. Now, this might look like maybe it could be something. And if you thought that, then you are correct. Let's look at the Pythagorean identity. Sine squared x plus cosine squared x equals 1. If I manipulate that just a little bit, if I move sine squared x over to the right side by subtracting, then now I have cosine squared x equals 1 minus sine squared x. And that I see in this equation. 1 minus sine squared x equals cosine squared x. I have a 1 minus sine squared x, so I can change that to cosine squared x. And then just some simple multiplication, cosine times cosine squared, that squared kind of looks like a bigger 2, there we go, is cosine to the third x, and that does equal cosine to the third x. True statement? Done. So on to the last two options or methods. When working with identities where there are fractions, you can combine using algebraic, or sorry, you can combine the fractions with common denominators. You can get common denominators, what I'm trying to say. And then the last option is to factor, and we already kind of did that in the previous example. So in this last example, we're going to use all of our tools to try to solve this one. Again, there's not one way to do it. When I was working through this the first time, there were actually two ways that I saw, one easier than the other, but I still got the same answer. So let's try to play with this a little bit using all of our tools and simplify some of this stuff down so that we can prove this identity. So I want you to go ahead and pause it and try it, try to get started on it, and then come back and check where you're at. So the first thing I did on this one was, the only thing I could really change was the cosecant. So I went ahead and changed that to 1 over sine x. At this point, you might be a little stuck as to like, ew, that looks real ugly. You have several options here, but one of the options is to get a common denominator for the left side. Now, again, you might be thinking, ooh, that's ugly, but it is a little bit ugly, but it turns out. So if you can stick with the problem and just don't give up, keep trying, then you're going to get to a place where it's not ugly. It actually turns out really nicely. So that's one of my favorite things about mathematics is it can get really ugly in the middle, but it turns out nicely. And you're like, oh, it feels so nice. Okay. So to do a common denominator, our goal is to get these two denominators to look the same. And basically right here, since they don't have any factors in common at this point, you're pretty much just going to multiply them by each other. The other way to do this is, I don't know what they call it, but I used to teach this in my foundations classes, but you can multiply, multiply, multiply. So if you have done that and you want to do that again, you can totally use that. But I'm going to multiply this side by sine x, the other denominator, and this side, I'm gonna run out of room here. I'm actually going to fix this because that's going to get ugly. Sorry, by the other denominator, 1 plus cosine x. And that equals 2 times sine x, or 2 over sine, not 2 times sine x, 2 times 1 over sine x. All right, looks ugly. Promise it gets better. So I multiply this side by this denominator, and I multiply this side by this denominator, so that now my denominators are sine x times 1 plus cosine x and sine x times 1 plus cosine x. That was my goal. I wanted them to be the same. Now I can start multiplying together. On the left fraction, I have sine squared x over, I'm going to leave this not multiplied. It's going to help me later if I just leave it. And then on this side, I have 1 plus cosine x squared over sine x times 1 plus cosine x equals 2 over sine x. Again, there might be a much easier way to do this, but this is the way that I saw it, so that's the way I'm going to do it. I'm going to go with it. Okay, now I have a common denominator on the left side, so I can add my numerators. Sine squared x plus 1 plus cosine squared. Nope, I wrote that wrong. Cosine x squared, and it does matter, over sine x times 1 plus cosine x. Whew, goodness, 2 over sine x. All right, so on the left side, these are not looking the same yet, but if we just keep working, stick with it, just keep working, they're going to start looking the same. On the left side, I'm going to, you might think, oh, I can start dividing terms, but not yet. Because of this plus sign right here, if it were multiplication, absolutely, we can start dividing things. But since it's a plus sign right here, we're not quite done. We can't start dividing things yet. So on that left side, I'm going to go ahead and multiply this out. Sine squared x stays the same. If I were to multiply that out, that's going to be, I'm going to need to write it out for a second because my brain's getting crowded. 1 times 1, 1 times cosine x times 1, cosine x times cosine x over common denominator. Oh my goodness. It gets better. It's coming together. I'm starting to see something that I can fix. Okay. On the left side, I'm still trying to fix this because that's kind of a mess. But if you can see, what's sine squared x plus cosine squared x? That's a Pythagorean identity. So I can start consolidating some stuff, which is really going to help me in this problem. So this I can add cosine x, or sine squared x plus cosine squared x is 1. That's going to really clean up some stuff. Oh my, I'm running out of room. I got to go over here. I'm so sorry. 1, and then plus the 1 plus 2 cosine x over common denominator equals 2 over sine x. I keep saying that wrong. Okay, again, on that left side, I'm still cleaning up. 1 plus 1 is 2. Clean that up. 2 cosine x over sine x times 1 plus, I picked a doozy, 2 over sine x. Okay, numerator, again, some simplifying. They share a 2. I'm going to pull the 2 out front. Leaves me with 1 plus cosine x. Ooh, guys, look. Now we can start seeing the light at the end of the tunnel. Okay, sorry, I'm getting exciting. It's probably annoying. I'm getting excited. It's probably annoying. Anyway, my brain's like moving fast because I love this stuff. This side, now we have 2 times 1 plus cosine x over sine x times 1 plus cosine x. Remember at the very beginning, you might have been tempted to do some dividing here, but we couldn't because of the plus sign. Now that I have a factor times a factor and a factor times a factor, now I can divide those terms. 1 plus cosine x divided by 1 plus cosine x is 1. And I end up with, I told you, promised you, 2 over sine x equals 2 over sine x. Done. Equal. So I don't want you to be intimidated by this. They're not all messy like that, but I just wanted to make sure to give you a messy example in this lesson so that you can see that you don't need to be discouraged in the middle of it. If you can just stick with it and finish out the problem, it does turn out on these problems. They're going to turn out. They were made to turn out. So, and then you'll probably, once you start to see the light at the end of the tunnel, like I did, probably get excited, a little bit annoying, and then turns out. All right, so to summarize this, we have some methods to verify or prove identities. You can work on one side, you can rewrite expressions, you can factor, you can get common denominators and add fractions, but the goal of all of those options is to get both sides to look the same. And that's all I have for this lesson. I hope I was able to give you some tools to help you solve problems. If you have any questions, please let me know. I'd be happy to help, and I'll see you in the next one.